We got a good full agenda tonight. Public comment on the agenda, if there's any. We're going to hear about water demand projections from Carl. And then Bill's going to talk to us about potential future water sources. We'll accept meeting notes from the past couple of meetings. Going to get the second part of the PFAS story. Ernie's not here tonight, so that's going to shorten the Q&A, I know that. Well, it'll at least shorten the A. The Q, I hope it doesn't shorten. And yeah, that's our plan. Any questions? Okay. Where have we been going, right? We laid out this roadmap that takes us on the path to looking at potential adoption of the Water Master Plan update in July of 2027. And so in January, we started down this path with some interspersed virtual meetings. Thank you for your participation in those over the past couple of months. I know we've kept you busy with a lot of information to digest and looking for your important feedback. So in January, we talked about the overall capital improvement program process and prioritization of those capital projects. In February, we did a review of the existing scorecard from the last Water Master Plan, gave an update on that, and started talking about some ways to revise it, to make it, to adjust it to current conditions, current issues, maybe get a little more efficient at what we measure and how we measure it. In March, we talked about condition assessment, climate resilience, and then PFAS issues. And here we are in April. We're going to be, as I said, talking about demand projections, potential additional slides, and continued PFAS. And then you can see where we're heading over the next few months. So we're on schedule. That's the good news. Opportunity for public comment on the agenda. Seeing none. Future water demands. Carl, you're up.
Wanted to start with kind of the overall here, why we keep talking about these kind of different ways of looking at demands. So this is the high level, how we calculate it and where we're headed to try to give you the roadmap. And then we're going to dive into some of the details here. So we start over here on the left. We have historical data for the island-wide demand. So we know how much water is produced and consumed by BWS's customers. That's in million gallons per day, MGD. But then we want to do some math with that. We want to kind of normalize it down to things. So the first thing we do is we divide that by the BWS population served, and that gives us to per person consumption, or gallons per person per day, GPPD. Then we can take that number and we go into this calibrated demand model. And this is what we talked about last July. So we're going to give you a reminder of what that is tonight. But you have seen that before. And there we take that GPPD and we turn that into a model to get some ideas on what are the factors that impact those demands. So that's all the historical, getting data into understanding the model. Then we can take that model and move into the future and do projections. So we move to the right side of the screen. Now we change those metrics into the future conditions, what we think is going to be coming in the future. That gives us a future per person consumption in GPPD. Then we take that per person consumption, multiply it by what we expect the population to be via population projections, and that gets us to the future island-wide demand. So we sort of step down and back up. Just wanted to give everybody the roadmap.
When you talk about the overall projection and the amount that's going to be needed, you're talking about per person, and yet agricultural water is maybe more so, and it seems like it's totally out of that projection. Can you footnote that?
Yep, exactly. That's a really good point. We'll hit it in here, but we use GPPD, which is the gross water consumption for utility divided by the number of customers. It's just a way of, you're right, it doesn't distinguish those items, but it's a way of balancing out. Basically, that's what all utilities do, so it lets us kind of have an apples to apples comparison. It does miss some of the details there. And
so what it counts is the agricultural customers that are on BWS's potable water system. It counts all of that agricultural usage. It doesn't count the non-potable ag water, right? The surface water that's not part of the BWS system. So it's just looking at the demands on BWS's system.
So it's good for measuring change, but it's certainly going to overestimate the amount of gallons per person that's being used.
Correct. So we'll see it here, and I'll loop back when we see it show up. The historical per person water demand. Again, we take the BWS total production, we divide it by the total number of people, and that gets gallons per person per day. And again, gross. So that includes commercial, that includes residential, that includes industrial and agriculture. And then we start looking for trends. So there's two major trends that we're looking at: seasonal, so the year within the year. Obviously, more demands in the summer, less in the winter, and then long term. So over the course of years. So this is the historical demand in the last 30 years in the blue line in million gallons per day. And one big trend already jumps out, that the demands have come down even though population, which is in the green line, has gone up. Not something we've talked about before, but it is a key trend to note. So then when we do that math,
Why is it all jaggy?
so each of these is summer. So we have summer, winter, summer, winter, summer, winter, summer, winter. And then long-term over time, we've seen some long-term trends as total use across the island has changed.
So population went up until 2017, 2018. Is it truly going down on Oahu?
I think it is. Yeah,
Okay.
this
And-
was pulled data. Now, obviously, there's one thing to note. This is population served, so it's necessarily a little bit of an estimate.
Right.
But
And when I look at that, it doesn't tell me from the jagged line that demand is actually going down, because it looks like it's going down in relation to the population served going down. Is that correct?
since we see a high point, in the early 2000s. Kind of since then, the summer peaks have come down a little bit, even though population has come up.
It looks a bit like it's holding steady, but
Yeah.
maybe going down a bit. Okay.
Well, we'll do the math here, and here's where it really does drop. So now this is gallons per person per day, so we're normalizing by that population. So you still see the summer, winter, the annual change. But now it really shows that drop through the early 2000s.
We have another slide that we used when we were doing our going out to talk to the elected officials, and there was a steep rise through the 80s in water use, and we were up to well over 150 million gallons per day, and now we say we average 145, but actually it's usually well below that. In fact, last month it was only 120 million gallons a day because of all the rain we've had. What would help is if we had one of those nice little straight lines showing how things are going down. But you can, and there we go. Yay, thank you. I love it. There you go. So that really shows you clearly how everything is dropping.
So we can make some educated guesses of what's going on here, knowing things, big macro trends. But one of the things we wanted to do is take some of the things that we've noticed and load them into a model and try to do some statistical analysis on it. So we're going to talk a little bit about this methodology. This is called an econometric demand model. The factors we're using are mostly economy metrics and weather. Those are really the biggest ones we're pulling in right now. We take that chart of demands, we pull in a whole bunch of data, and we start testing which variables or combinations of variables give us a correlation with that demand to try to build a model. So we looked at dozens. These are the ones that we found had an impact, and the blue ones are the ones that really were the strongest impact. So you'll notice the first set here: max monthly temperature, monthly precipitation, previous month's precipitation, and consecutive days with no precipitation are all climate related. And those factored were pretty significant. Then there's a couple: unemployment rate, a metric for economy. We did look at a couple others like recession indicator and some others, but that didn't end up working quite correlating as well. Then we look at price of water. and non-revenue water. All of those tended to give us correlations that were significant. So once we apply this, so the orange line here now, this is the one where we're just doing math and trying to recreate that line. So we're using those factors that we came up with against the data, all that historical data that we used to come up with the correlations, and that gives us that orange line. So that's modeled versus the blue line, which is the actual. So this tells us, all right, we have a model that's reasonable. It's not perfect, but it's reasonable. It does a pretty decent job of following the major trends. These are those ones in blue that I called out. So what this means, the coefficient tells us how much the water demand would change if that variable changed by 1%. So the top one there is the monthly average daily max temperature. So if that increases by 1%, then the demand would increase by 1.05%. Do another piece of math here. The volumetric price of water, if the price of water were to increase by 1%, then the demand would decrease, because it's a negative, by 0.18%. Now, one thing I want to point out is that that is a smaller coefficient than the max temperature, which is at 1. However, the max temperature is varying by lower percentages than, say, the price of water might. So just the size of that coefficient doesn't necessarily mean the amount of signal you're going to get from that. All right, so that gets us to having a model that we think works. Now we're going to move into the projections. We use this demand model. We take those, we try to make an estimate of what those factors that we're looking at will look like in the future, and project those out. So we're using these same coefficients, and a big one is, those climate factors. You all heard Sebastian, that was a little while ago now, maybe that was last April, talking about some of the climate projections that we did. That's a big part of why we were doing that, is we were getting these numbers to be able to feed back into this. So we projected out. We used 3 different climate scenarios: low emissions, moderate emissions, high emissions, trying to get a bit of a spread on what those look like. Unemployment rate, if anybody can estimate that, let me know. That we're just taking out into the future as flat, because we can't really know what that is. Same with non-revenue water. So these two, while they correlated well in the model, there's not really much we can do to project those, because we don't really know what's going to change there. So now if we project this out, all other things being equal, let's look at just the climate.
Is that the jagged line that we saw from the historical data on the previous slides?
Correct. So this chart is demand in MGD. So this is total demand. And over the last, what is this? This is 60 years here or more. Within this green lines here, there's actually 3 lines in there, and that's the 3 climate scenarios. So it turns out they're overlaying each other pretty close. So in this scale of chart, you really can't see a whole lot of difference, but all 3 are there: the low, the medium, and the high emission. So this chart is if we look at just the climate side of things. So everything else being equal, we're assuming today's population is just flat. We're also assuming no rate increases. So that means that we are actually losing the purchasing power. The board is losing the purchasing power by inflation. So that's not null to inflation. That is actually 0% rate. So that would assume, the cost of inflation losing buying power. So if we look at just that, we see, which I think is intuitive, a slight increase in demands going into the future, as we know from the climate modeling that temperature going up slightly, precipitation moving around a little bit in the year, but probably overall coming down just a little bit. So that sort of makes sense. Now let's look at population. So we're going to lay in just the population increase. So we're using the Department of DBEDT, Department of Business, Economic Development, and Tourism. There we go. We're using their numbers for projecting population. So it's a pretty low increase. It's, I think, about 3.5% over those 30 years. It's pretty low. But it is going up, so we would expect that to increase demands, all other things being equal. And we see that. Now, if we lay on a 3% rate increase, so what we're trying to use there is just adjusting for inflation. So kind of a null purchasing power rates there. That's what we're trying to keep. And that actually flips the sign on the slope we start decreasing into the future. So that is the most significant factor that we're getting, pushing those rates, or pushing the demands into the future.
So on the climate projection, you're saying the rain is going to go down a little, but it's going to come in different ways. Like it used to come more consistent, which would probably lead to less water consumption. Its modeling, as I understand it, is going to be big downpours like we just saw, and then stretches of dryness. So even though you're getting the same volume, so are you calculating in that rainfall projection the variability?
Yes.
That's gonna, okay, so it's not just a straight
No,
numeric.
it uses those factors of the consecutive days with no rain, this month, previous month's precipitation, max temperature. Those
Okay,
are the
great.
four.
And then on the population, it looked like if there's a downward trend on population, how is the projection that the population's going up? That's just a DBED number?
Yes, it's a DBET number. So that's the best we can guess at.
Okay. And then the final question would be around the rates. Are these the rates that are already been passed and baked in? Or are these, this is a model projecting continuing those rate increases beyond when this phase stops?
This is already baked in for where we're at now. This is assuming adjusting for inflation going up.
3% rate increase per year throughout the duration of the model.
Yeah.
For rate increases, we're not looking at the standard normal rates that we would see for increases. This is 3% over and above what we have now.
No. It's just assuming a rate increase of 3% per year, period.
Okay, which would be equivalent to what we would in the past have said normal inflation is 4% a year. We're looking at just 3% now.
Yeah, basically it's just an assumption that says if rates went up at about the rate of inflation through this projection period of 30 years, that in and of itself would drive water demands down.
So if it's $1 per 1,000 gallons today,
Yeah.
and next year it'd be $1.03.
Uh-huh.
And that 3 cents is not made up of inflation,
Well,
or is it made up of rate increase?
It's a rate increase, right? The buying power of it is offset by inflation, right? Because if inflation is also 3%, then you didn't gain anything.
Because I'm looking at it as a rate.
Yeah, it's a
rate
3%,
without-
3%, forget inflation for a second. Let's
Okay.
take that out of the equation.
So it's not
the-
inflation,
The rate of it is equivalent to inflation.
but it is not
It is
the
not inflation.
inflation rate.
It's the
So
rate going up.
The inflation rate is on top of this.
No, forget it. Inflation doesn't matter in this. We probably shouldn't have confused it with that. It's the cost of water going up 3% per year.
Okay, minus inflation.
No, it's the cost of water. It's your bill going up 3% per year. Yeah,
I get it, but somewhere along the line, you're going to have to talk about inflation.
agreed. So
So this is
it's-
minus inflation then? This is just a standard increased rate of water?
It's just the price of water going up 3% per year.
And-
Inflation, right?
Wait, but I'm
if
trying
it-
to get to the point.
Sure,
The 3% is actually a rate increase.
yes.
Okay, that's what I wanted to be clear about. This is a rate increase minus inflation.
It's the latter part that I'm not understanding.
I can charge, if I have $1 today,
Yeah,
and tomorrow that dollar is worth 97 cents,
we're not accounting for that.
okay, got it. I just wanted to make
Yeah.
sure what you're accounting for and not accounting for.
So it doesn't, if rates increase at about the rate of inflation, to your point, you don't get any additional buying power, right?
Right.
You can't go replace more pipeline than you were before.
clarify something. If it's 3% per year, and the rates have been raised in a 5-year period, usually in the past, so is that 15% over a 5-year period? The cost of delivering water is not, you're not paying for the water, you're paying for the water service. You're not paying for the water because it's a state adjudicated principle. The water is not a cost.
It's your bill.
It's the service that you're paying for.
It's your
Yes.
bill going up.
Correct.
Yeah. And what we see in the model, right, when we went and did all this regression analysis that Carl was talking about, is that we see that when rates go up, historically, that part of that downward trend in water usage is explained by rates going up over time.
There's frequently when people are projecting, there's the best case, worst case, and somewhere in the middle. Have you worked out the variability that might be as reflecting some probabilities with regard to that kind of a spread?
That's kind of what we were trying to show here is the impact that each of these have. I'd say this is probably a pretty decent, spread of where we'd expect things to go. So it's relatively minor increases and decreases. I mean, this is over 30 years, right? So these are not, demand isn't going to the moon or dropping off a cliff. It's staying relatively straight, which is good for planning. Anything else here? All right. But to this point, there's some limit, right? There's some limit where even as things change, as rates change, et cetera, that demand hardens and we just stop getting that signal, right? As rates go up, eventually people are just using what they need to use. So one thing, because we're looking at rates, we're necessarily extrapolating. We're going outside of the historical data that we have. So there's always as we get further away from that, it gets less and less certain. So one thing we wanted to eyeball was, okay, this takes us down to, you're going to see it, but it takes us down to about 125, low 120s gallons per capita or per person per day. And is that reasonable? Would we get demand hardening before that? So this looks at some agencies across the western U.S., and this looks at their gallons per person per day. So you can see BWS right now is actually right about smack in the middle. So there's a couple things this tells us. One, it says that, and the most important thing, there's probably room to go. There is efficiencies that can still be gained via conservation, reduced outdoor watering, things like that. That's really what we're seeing here. So coming down to that mid 120s is very within the realm of reasonable. So whether we're going to get there or not, but that just tells us that our model is not unreasonable.
You know how the sewage is tied in with our water bill part? Do you think the demand is dropping because the sewage cost is, kind of high? Not necessarily the water rate went up, but that they look at their bill and they say, oh, this is now more expensive, and it's not to do with the water rate going up, but it's got to do with the sewage rate going up. So then my question is, how we talked about in the past, perhaps that the sewage rate will be kind of separated out. Maybe they might go on their own and assess us separately. If that happens, then will the demand really drop that much? Because when I look at the sewage one, I don't even look at it separately. I just look at it as one big bill. So when I see that go up, I'm like, oh my gosh, yeah, then I'm going to stop using as much water. But it's the sewage that's really expensive. It's not really my water consumption that's expensive for me. It's my sewage. So
I love that you're asking these questions because they're the exact questions that I asked Carl when he and the team came out with this analysis initially, was exactly that. And so you went back and looked at all that, right?
We did. We went back and we loaded both into the model. One thing is those two rates are actually, we call it collinear. They tend to move similarly to each other. So in the model, the statistics did a hard job of teasing out the difference between the two of them. So you're probably right. It probably is the total. But we didn't have a statistical way of teasing those two apart just because they're moving together.
And given the municipalities that you've chosen, some of these municipalities have other incentives, especially like in LA. If you get rid of all your grass and you either put rock, which is worse because then your heat goes up in your house, or you put artificial turf down, that also provides for a lesser need for water from a landscaping standpoint. So have you taken that into consideration here? Because you're projecting, 120,000 sounds reasonable that we could reach, but is it based off of similar incentives, if you will, between municipalities?
Ultimately, we don't know where we're going to want to head. Maybe, it's partly for this group to provide input on do we want to be providing those incentives to drive that conservation? Where do we want to go? That isn't a sure thing yet. So this is more looking at where could we end up based on where we see the trends going right now. Yes, a lot of these, that's how most of these utilities have gotten down that low.
It's like, when I lived in Tucson, I had no grass.
Mm-hmm. Yep.
My yard was complete, essentially clay, and where I had trees is where I used water. Or, my cactus or whatever, they'd get watered once every God knows how long I would water it. But other than that, I used essentially no outdoor water. It was all indoors. And, you don't use very much if it's all internal.
Yep.
So that's why I was asking, because I know the different situations in some of these municipalities, and I'm wondering if we're doing an apples to apples comparison.
It's not meant to be an apples to apples comparison. It's just meant to show that there's a range of GPCD, of usage across different municipalities, right? You mentioned Los Angeles and their incentives for taking out turf. I think you'll be happy to know that you can't replace it with rocks anymore and get their rebate. It has to follow really stringent standards for what it gets replaced with. Las Vegas similarly has a very aggressive turf replacement rebate program, but you can see that their number is still very high due to that outdoor water usage. So, no, it's however, like the Bay Area, that Bosca one, right? So that's in Northern California, a little wetter than Southern California, so you're probably seeing the result of that increased precipitation. Again, not meant to be an apples to apples comparison, just an illustration of the range of numbers across different utilities.
Topic of what she's talking about, alternatives to grass, and this may or may not be a question for you guys to answer or not, but do you happen to know if, how they talk about like the astroturf kind of stuff, having a lot of the PFAS kind of thing, is that true?
You should ask our PFAS presenters later in our meeting today.
So now that was all discussing island-wide, so we need to get a little more granular with it. So one of the things we use a fair amount on the island is Department of Planning and Permitting's development plan area. The island divided into more or less 8 spots, well, exactly 8 spots. Why are we doing that? Across those 8 regions, there's climatic differences, there's demographic differences. I mentioned the difference between commercial, industrial, and residential proportions, and then agricultural water use. So all of those vary across those. So we want to tease out a little bit what might be happening. So now we're going to start with what it is today. So this is 2024, I guess almost today. This is the gallons per person per day across each of these development plan areas. So a couple things I want to point out. Most of them kind of center around that 140 or so. It's kind of a fairly decent median, especially the more developed ones. And then you see North Shore and Waianae that are significantly higher. Why? That comes back to that gross water use. That's where there's ag meters on potable supplies. That's where they're showing up. We're getting that extra. It's not that people in North Shore or Waianae are using more water. It's that there's ag meters pulling from potable, and we're still dividing by the same number of people. So that's why those are higher. Central, similarly, is actually significantly lower. I'm not entirely sure what that is. I think it's probably an artifact of some waters moving around. It's, these designations don't follow the water system. There's some where it's pretty easy to separate the system in two places. Central is one where, especially this boundary between Central and the primary urban center, is pretty hard to get exact divisions between. So, all right, so that's in 2024, but now if we project this out, okay, what are we looking at in the future? So this is now into 2055, and generally we're seeing about 13 to 14% decrease. And the reason those are pretty similar is that the cost of water is the biggest contributing factor to that decrease in GPPD. Now, there are some caveats here. The climate is what is making them slightly different from each other. But as Bob asked, we don't really have great visibility into the ag meters in Waianae and North Shore, at least in this analysis. So there is some caveats here, but this is generally where we see happening. So the island-wide, it goes from low 140s down to low 120s is what we're seeing over the next 30 years as a target.
Data centers, any other like big user military? Is there like other potential like large mover water users that may come online separate from just like a regular linear commercial or residential increase?
We are using the developments that we know are coming in are in there. But that said, that's looking out a couple of years maybe. Beyond that, we're really just looking at the population increases. Any specific things we don't really have.
Since we're projecting decreased shift in, consumption, does that mean that things like the construction in progress, those kind of jobs trend downward too? In regard to maybe, we don't need to drill X more wells because we don't anticipate needing to pull on that many more resources? Does that correlate with that?
That's an excellent question, and Bill's going to talk to that in about 5 minutes.
These projections, are they pushed through the filter of the general plans and the sustainable communities plans that relate to population fluctuations and land use, zonings and things?
No. And
Thank you.
So this is really a gross look into way into the future. The one caveat I'll give to that is we are using the DBIT projections, and those do, on a gross perspective, they have those in there. So as the population changes.
Carl, Bob, when we do our watershed management plans, we do use DPP's projections. That's the next level down from the water master plan, which is kind of the 30,000 feet level. Then we get into the more details.
One more question on what you have up there on the charts. So you're showing Waianae going from 183 to 158. Currently, BWS is attempting to get us to be a water management district area through Seaworm. Does this take that into consideration or not?
No.
Okay, thank you.
All right, so then the next part, so that's of the gallons per person per day. So then we need to look at population changes. So this is where what comes from DBET. Looking over through 2050, they go through 2050. We extrapolated another 5 years just to get to the marker that we needed. But generally, this is what they're calling out. So most of the growth, or all of the growth, is really down on the south side of the island, decreasing populations throughout the rest of the DP areas. Overall, I mentioned it's a minor growth island-wide. It's 3.5, 3.6% over that 30 years island-wide. But it's centered on the south side of the island. So if we take that gallons per person per day times this many people, we get to these demands. So this is where we're shooting out into that 2055 on what those demands might look like. So now we're in million gallons per day because we've multiplied those back together. We're back to the far right top corner of the chart that I showed, or the first slide that I showed you. So here we're showing generally across the island decreasing total demands, with the one caveat being EVA, where the population is increasing enough that it offsets the lowering gallons per person per day. Again, I want to use the caveat that especially in North Shore and Waianae with the ag there's probably a little bit more uncertainty in that decrease than some of the others.
What you expected? How does it compare with what you would have thought water demands would be projected to do out into the future?
I'm just wondering about the East Honolulu projected decrease is relatively small.
So there's still some growth in East Honolulu, which is why it's not the same level of reduction. So it's the GPCD is still going down, or GPPD, sorry, but population is going up. So those are offsetting each other somewhat.
We found out in our last storm that came through here that meteorological prognostications can vary a great deal. So when you're projecting out 25 years or so, and with weather change being predicted as a significant variable, which you pointed out in the very beginning, how heavily is that factored into these projections?
There's a reason we did this 10 years ago with you all, and we're doing it again. What we're really trying to do is make sure we're directionally accurate, and we keep updating as we go. So I promise that this is not the number that we're going to hit in 2055. Hopefully it's somewhere in that window. We want to make sure that we're keeping ourselves pointed in a window that is reality, not trying to nail a number for 30 years out. All right, so what we're looking at next, so this was kind of a gross cut. There's a couple things. One of the nearest term changes is the TOD development. So that's less about the overall demand across the island and more about how do we get water to those spots. So it's a little bit more of a local analysis. So we're layering that in. There's some potential housing, the affordable housing project impacts, kind of a similar thing where you're getting a relatively concentrated demand in a new spot. And then we're taking all of these, and this is what we're going to talk about next, and using them to inform the source evaluation as we move forward through the master plan.
Carl did a good job of showing that not only, we are having demands going down in general, and the charts that showed the demands being reduced over time are annual averages, but we also saw a lot of variability, a lot of year-to-year differences. If there's one thing over the last month have taught us, rain can be very different, and that definitely affects demand, like we saw in the analysis. So you might be wondering, demand is going down, why are we talking about future water resources or future water supplies? There's still planning to be done to address that variability, that uncertainty, the year-to-year differences. And also, if you're looking to have a comprehensive water master plan, you want to be able to look at sources that you could use in the future if you had to. So we're going to be doing that today. I'm going to talk about what kind of stresses might cause a need for supplies in the future, and then talk specifically about a pumping capacity analysis that shows the need very clearly. And then we'll talk about options for alternative supplies and what those look like, things that others around the nation and world are investing in, and could be options here. And then I'm going to finish with a little treat, public education video about water reuse. So talking about need for new supplies. So the demands that were the first part of the presentation are one part of the equation when you're talking about supply need. Of course, if there is a supply need, it's going to be the difference between how much demand you have and how much supplies you're meeting that demand with, right? So if there's a deficit in terms of your water supply, you don't have enough, then you have to start looking to operate the system differently or looking for new supplies to meet that additional demand. So I wanted to talk about the stresses that might cause a need in terms of the water cycle. And you guys have seen this kind of chart before. It's a graphic of the water cycle where you have precipitation driving recharge into the aquifers that we use for supply. Some of it leaks out to the ocean, right? Some of it we pump to meet demands. Most of it ends back out in the ocean one way or the other and starts the cycle all over again with evaporation. But talking about different stressors within this cycle, right? So starting off at the top with precipitation, rainfall, and recharge. Climate change can certainly affect the amount of precipitation occurring over time, and that was kind of shown with the high, medium, medical scenarios that we looked at, right? And as we've seen recently, more rainfall falling as storms and very concentrated events causes more runoff and reduces actually the amount of recharge that you can get, because if a storm comes every week, ground's already saturated, you're not going to get much recharge on that second event, right? And then as less recharge over time happens, this will reduce the amount of water in our aquifers that we use for supply. And so that may affect, if it happens, if there's a deficit over a long enough period, that may affect the safe yield of the aquifer, the amount of water that you can consistently get out of that aquifer year after year after year. So you may have to take that into consideration. Moving to groundwater quality, we heard, myself have presented in the past about how groundwater quality can affect how much water you can get out of the aquifer, right? So that can be affected by contamination, whether it's point sources, right, a spill, or if it's legacy ag chemicals, from decades ago, that can all have an impact. And then we also talked before about overpumping at supply wells, because there is this salt water that our freshwater wedge is sitting on. If you pump wells too hard, that salt water gets drawn up, that brackish water, and can reduce the amount that you can get out of. And there's always, things that happen along the way. I mentioned contamination. There's, sea level rise is also, a stressor here. Nobody could have predicted what Red Hill would have done to the system and the groundwater there. So these things you need to plan for so that you can adjust when they do happen. So groundwater pumping also is a stressor, right? So that's dependent on the amount of customer demands, as we saw with Carl's presentation. But like the presentation or the graphic that showed how demand is changing around the island, it also matters if your supplies, your wells, are in the right spot to meet demands and how demands are evolving over time. So relating all of those stressors back to the water master plan and how we choose, we're going to incorporate it into the plan. We're looking at, is there a water supply and water infrastructure available to meet demands where they're happening and how they're changing? Sometimes new infrastructure or new supplies are needed to meet those demands and how they change. And so we've got some arrows here. So if in the case that overall demands are going up, whether it's in a localized area, there were some, or maybe just one area that Carl showed is going up in EVA, the demand. If supply yields go down, then we'll need new supplies to counteract that. Or if demand is shifting around the island in a way that infrastructure can't handle, the existing infrastructure, we're going to need infrastructure to take care of that. So I wanted to talk about a pumping capacity analysis that we did. And this is looking at infrastructure around the island that BWS uses to serve demands, and whether it's adequate or whether there needs to have some augmented portions around the island. What we did in this analysis is we compared demands to the firm pumping capacity at each of BWS's 110 distribution pressure zones. So we went zone by zone and looked at, do we have enough sources, supplies, pumps, conveyance to meet the demand that are in that pressure zone. And we identify where pumping capacity isn't sufficient and where infrastructure may need to be augmented there. So in this analysis, there were 5 pressure zones out of the 110. So, overall doing very well, meeting demands, no issues. But there were 5 pressure zones that could use some additional either pumping capacity or supplies. And so the solutions there is either to bring new sources to that pressure zone or to transfer water in. So this is the kind of analysis that we're looking at this is infrastructure focus, right? So we're not looking at rainfall, we're not looking at aquifer yields. This is infrastructure focus to try and identify where we might need additional sources or water brought in. So I wanted to talk about some alternate supplies, and some of these actually aren't alternative. Some of these BWS is already investing heavily in, but I wanted to talk about the range of supplies other than groundwater pumping that could fill the gap in any of those situations where we need water. So I want to talk about continued investment in water conservation, always a key part of plans going forward because it has been a fruitful effort. Seawater desalination is going on now, working on that, so provide a small update on that. Stormwater capture and aquifer recharge, and again, we're not looking at low-hanging fruit, we're picking all the fruit at this point, right? So we want to look at all the options available to us. And then we'll talk about centralized water reuse or recycled water, and then talk about some on-site reuse that can and is already planned for happening in Hawaii. So on the water conservation side, Lorna and her crew at BWS do a great job in promoting and investing in water conservation. But there are some core BWS programs that they're always running. The first one, WaterSense, is looking at EPA's views on water conservation, but also it's kind of the rebate program. So looking at residential and commercial rebates to switch over to low flow devices. They have a trade ally program where they help businesses improve their water conservation and save water and link them with vendors that can help them do that. And then Water Wisdom is their term for their auditing, and that's when they work with a residential homeowner or a business to really take a deep dive into their usage and find ways that they can cut back on water consumption. One thing that's new, continued investment, is E&V, which is the sewer agency, right, wastewater agency, has joined in for a joint rebate and effectively doubled the amount of rebates, doubled the value of rebates, so that we can maybe force more people or entice more people to make these investments in replacing their fixtures. And so these are just some examples. Toilet went from 100 to 200, replacing it with a low flow toilet. And all of these really are double what they were previously. So that's new program. This is highlights from the rebate program from 2018 when it really got up and running. And since that time, or within that span, they saved 117 million gallons per year through the rebate program. And that's 21,000 rebates issued over that 7 years, and $1.6 million rebates provided value. So a lot of great stuff. You can see the breakdown between clothes washers, which is the big ticket item there, toilets, rain barrels.
So that value, if you do the math, I guess, is like $70 a gallon, like rebates provided and gallons saved. How does that value compare to how much it costs to pull additional water or provide it through desal?
The cost for new supply, like if you were to put in a new well or develop a brand new supply, is, what was it now, 10 million per million gallons? Does that sound right? It used to be 8, but that was a while ago. And can vary from supply to supply, right? So desal is going to be higher because it's, just a more costly investment technology-wise. Yeah.
Bill, Josh, conservation is still the most effective and cheapest way. Yeah, all the other ones cost, unfortunately, especially right now, it gets very expensive. I'm sure Mark has comments on desal.
How much does it cost to drill a new well? So say, how much does it cost to drill a new well?
It's running us between 5 and 7 million right now. Yeah.
And then so a desalinization plant, how much does it cost to do that?
A lot more.
Jicky, we can get that number, but it's not inexpensive, it's really expensive, but we'll get that number.
Wanted to highlight some items from the Kalaeloa seawater desal plant. So it uses a reverse osmosis membrane to treat seawater that is in the deep aquifer, so below the freshwater aquifer, pumped up. And it's designed to treat 1.7 to 2.5 million gallons freshwater per day, provide that. The idea is that it will serve Campbell Industrial Park, Kapolei Business Park, and the Deep Draft Harbor. I mean, it's located right in Campbell Industrial Park. So these are close by demands it would serve. Yeah.
Okay, our head of capital projects over here, Jennifer Failer, just told me it's running about 240 million right now, but it's probably going to go up. So just to give you guys a ballpark. Thank you. Thanks, Jennifer.
The disposal of brine after the water, after the salt is removed.
Yeah, so the disposal of brine is going to be shallower wells disposing into the brackish aquifer.
Or cap rock or something like
Yeah,
that to
cap
contain
rock.
it.
Yeah. So that's all included.
So the installation of that process, is it being duplicated from another area of the continental U.S.? For the design and the company that's doing the implementation?
Yeah. So it's actually the design of and construction is a coalition of companies that include, mainland and companies and local companies, but using tried and true technology that's been deployed elsewhere.
So it's met all the environmental concerns that normally come along with that?
Yeah,
as far as
so
getting
they
approvals?
They just had the treatment evaluation phase mid last year, end of last year, that showed the treatment, proved the treatment is sufficient to meet all regulations and water quality standards. Yeah.
So there have been environmental impact studies done out for the public for consumption? Okay. And that's already been completed already?
Yeah.
And there are no further EIS studies being done in order for this
All that
implementation?
permitting is completed.
Okay, thank you.
I had an opportunity 2 weeks ago to have a conference call or meeting with a company called Ocean Well. Are they familiar to you all? And I was wondering if it sounded, all too good to be true, but it was pretty interesting. Subsea desal using ocean water pressure from deep to, reduce energy consumption, brine disposal more offshore, so that kind of thing. And they're looking at, they said they're considering or maybe close to putting one of their cells off Natural Energy Lab, Kona. They're looking at a project off Vandenberg Space Force Base, and then sounds like they're either close or have something going on with some Southern California communities. But I'm just curious your take on that technology and or that company.
A comment on anything
Okay.
about an individual company, Mark?
That technology.
Yeah. No.
Thanks.
So,
One of the large costs of operating desal is the enormous pressure that you need to create to push it through the membranes, right, to do the filtering. And so that's where that idea comes from. If you had the pressure driving from deep in the ocean, you have to be pretty deep. I think we looked at it, it was like 400 plus feet deep in the ocean. So there's places that will work and places that won't, just based on the depth. But that's the idea is to save on that, creating that pressure to push through the filters.
I understood that to be the technology. I was curious if you had an opinion on the technology. And if the answer is no, or you don't want to have an opinion on the technology, that's okay too. All right, thanks.
For the desalinization plant, is that green energy that you're utilizing, incorporating into that technology?
I don't know what the plans are for energy. I don't think so, no.
No, not right now.
So I wanted to put in a plug for stormwater capture. So we are, BWS and CDM are working on a project in Nu'uanu Valley. And we've been looking at conveying excess stormwater. So stormwater that would, make its way eventually to the ocean. Conveying that from Nu'uanu Reservoir 4, which is the big reservoir that you drive by when you go over the Pali. And then using some pre-treatment and also using the elevation down Nu'uanu Valley to our benefit, creating some hydroelectric power as well in the project, but basically moving that water down the valley and then eventually, once it's treated, injecting it into the aquifer for aquifer recharge and further use once it makes its way down gradient to the Kalihi wells, which are down in Kalihi. We're currently developing a preliminary engineering design and doing an environmental assessment for that project. But this gives you an example of a stormwater capture project to utilize that stormwater, excess stormwater. DFM is actually going to be starting up a stormwater master plan soon, and they'll be looking at a whole range of different beneficial projects to green infrastructure and those types that may increase groundwater recharge and actually manage runoff as well.
I just want to say that this is awesome, and it's a nice little comeback because Nu'uanu is where the hydro renewable energy was captured to power Iolani Palace in 1890, which was, one of the first buildings to have electricity in the world. So to come back and do this with the water and the hydro and generate electricity is.
There's still parts of the building, generation building in Nu'uanu when you go, where Princess Kaiulani flipped the switch to turn it on. Yeah.
Stormwater isn't necessarily very clean, and you talked about cleaning it up. How would you do that? You're not going to use reverse osmosis on that. What are you going to do to clean up, I'll call it dirty stormwater, because it's pretty brown sometimes?
Yeah, so the idea is to not have, very expensive, high-pressure treatment involved, because you can kind of pick and choose when you take water from the reservoir. So you're not going to take it when it's, chocolate milk, for sure. And you can wait until that settles after a rain event and take water off the surface where it's probably cleaner. If you do that, then you can get away with cartridge filters, which are, a lower level of filtration to filter that water. Yep. I also wanted to talk about centralized reuse. So this is recycled water reuse that most people are familiar with. This is a diagram that shows kind of the flow of water as it's recycled, starting off in, I don't know if this works. You are here, this is your house. Your wastewater makes it to the treatment plant. Some of that all of that is treated, and some of that makes its way out to ocean outfalls. But there is opportunity to take that water and with filtration and disinfection, use it to irrigate, and that's what's being done at Honouliuli right now. Also, you can treat it a little more highly using that reverse osmosis that we talked about, and use it for industrial uses like cooling towers and processed water and stuff like that. Honouliuli, there is a water recycling plant out there, and they are doing about 7 MGD of high quality R1 water, and that's for a lot of landscape irrigation. And the RO water is a smaller system, but that's used, as I said, for industrial uses, about 1 to 2 MGD of that. There are other kinds of reuse, and so I wanted to touch on those. The first is indirect potable reuse. Instead of sending it to irrigation, you do add on advanced treatment onto your train of treatment. And indirect is called that because it uses an environmental buffer. So they either take that water and put it in the ground or put it in a reservoir where it sits, has further in situ treatment, and then that is used by to supply a residence or business. That's indirect potable reuse. There's also, you may have heard of direct potable reuse, which replaces that natural buffer, that groundwater aquifer or surface water reservoir with more treatment and treatment of a high enough level to be able to then use that water directly in a residence or business. So that's direct potable reuse. I wanted to mention some things that are happening right now in terms of reuse, and that there is a Bill 21 being looked at right now that amends the land use ordinance to basically incentivize gray water systems when planning in the TOD areas. So that's being considered right now. Department of Health has regulations for gray water use. They do not yet have regulations on IPR or DPR, direct potable reuse, but it is something that they and others are working on right now.
You know, the Japanese have a toilet that has a wash basin on the top. So you use the toilet and then you wash your hands afterwards when you flush. Why hasn't that, to me, that's like using gray water reuse.
Yeah, using it twice.
But I don't see anybody or anywhere where these toilets are being used. Why?
I don't know the answer to that. But
Have you seen it? Have
yeah.
you seen one of those toilets? I think they were awesome.
Yeah.
Plumbing code issue, Helen. I suspect it's an issue with U.S. plumbing codes.
So I did want to mention a development that's going up right now in Mo'ili. It's on Kapiolani, kind of by Iolani School, and they're using a treatment system that is going to capture gray water from sinks, showers, and laundry in the building and reuse it, saving up to 30,000 gallons per day, using it for toilet flushing and irrigation of the property. Yeah, it's 1,000 units.
Holy mackerel.
Yeah.
I didn't realize that.
Yeah. So got some lofts and a tower, or a couple towers.
So Bill, that's including their air conditioning, water from that in order to contribute to that gray water?
I don't know. Cooling towers weren't in the mix when I read about it. Yeah, so I didn't see actually recycling of that. It's mainly the toilet flushing and irrigation. Yeah, I don't think they're getting it as high enough quality to be able to use in the cooling systems.
Oh, I mean the excess from the cooling systems to use the water from the air conditioning systems that drip water to be utilized for
Condensate. Yeah.
the condensation
Yeah,
that's
perhaps.
being incorporated.
It wasn't listed specifically, but perhaps they're collecting that as well.
Is BWS, are they developing a video based on the best practices of this Kuile place to be able to incentivize other builders to incorporate that technology?
So they've been part of
Sorry, Ken.
part of the mix, but yeah, they're not doing anything special to incentivize it. But you're going to be seeing more and more of it, I would think.
So the reuse on the expense for ultraviolet disinfection can be pretty expensive. Does that get just passed on to the homeowners? So it's the cost of the water plus the cost of the treatment. And so the real question is, how cost effective is this kind of reuse?
Yeah, I don't know the cost effectiveness. It is definitely saving them money overall. So the cost of the system paid off over time, of course, plus the maintenance and the operation of it is still going to be less than the money that they're saving from the water savings.
HFDC, for example, looking at this kind of building, what kind of plumbing does it require?
So it has to be dual plumbed from the get-go.
Right.
Yep.
So again, back to my question about affordable housing as opposed to luxury residential projects. If we are pushing for affordable housing to have dual water systems, plumbing, the chance of doing this kind of saving increases. And what about individual homes doing this? Dual water systems to flush toilets and so on, catching water off their roof.
Yep. So there's rain barrels, right, that are one way to conserve water at home. Because there's regs in place, you could you could have a small gray water system at your house too that catches off the laundry machine or, sinks. So that's something that is doable now.
So with population expected to increase in places like Eva in the future, shouldn't all housing build in that kind of dual water system, water catchment and so on?
I think it goes back to the payback and whether or not the development is dense enough to make it worth it.
Mm-hmm.
When you have units stacked on top of each other, it's less piping than, throughout a flatter development maybe.
Right.
To get the kind of developer buy-in that you need, funding that you need to develop something, affordable housing by way of example. I mean, realistically, I'm not trying to be pessimistic, but realistically, they're not going to want to spend that kind of money on, affordable housing because the point is to build volume, and it's important to save water, yes, but it's an expensive endeavor. And so just to get the funding for affordable housing is a challenge. And I know that, one, I work at the Honolulu Board of Realtors, right? So affordable housing is definitely a challenge in the state of Oahu and the state of Hawaii. So, but I can tell you from being in the room with the developers that it's definitely, hard to get developers to fund these projects. It's a costly endeavor. So I can see why somewhere like a Kuilei Place can afford it, because that's private more than trying to house local residents that need affordable housing versus I'm willing to spend some, higher dollar amount premium.
I just wanted to mention there is an example in San Francisco that uses actually the same system that they're going to use at Kuilei Place. But this is a system that treats black water. So it actually collects from the entire building. So this is the Salesforce building recently done in San Francisco, and they collect from toilets and urinals, and so everything treated, and again used for toilet flushing, and this uses circulated in the HVAC system. So we'll close with a quick video here, 4 minutes.
Video that was recently put out by the Southern California Water Commission, Water Coalition. It's available on the Water Reuse Association's website, and it's kind of a introductory primer to water reuse that we thought you might find interesting.
Water. We all know how essential it is when it's in our hands, when we're putting it to use in our daily lives. But where does it come from? And where does it go after we use it? Technically speaking, water doesn't really come from or go anywhere. All the water that has ever existed on Earth is still here. Nature knows that water is too precious to use just once. Every drop of water has been on an incredible journey, used, recycled, and reused millions of times for billions of years. Even the clearest, most pristine drop of water was once something else entirely. It's hard to believe, but this is exactly how nature works, using, reclaiming, and purifying water in an endless, sustainable cycle. Essentially, that means all water, yes, all water, is recycled. For thousands of years, humans have followed nature's lead, developing ways to speed up and improve the purification process. From ancient sand filters to today's advanced purification technology, we've continued refining how we clean and reuse water safely. Here's the reality. We're not getting any more water. Yet the demand for clean, reliable water keeps growing. Our changing climate is creating more water-stressed regions where bringing water from hundreds of miles away is a less reliable option, and a natural disaster could cripple water delivery systems. This means communities across the world need sustainable ways to secure safe water. Water suitable for many different purposes, such as drinking, bathing, and growing food. Because every drop of water has value, even wastewater, which is technically just water we've already used, can be cleaned and purified to remove everything from microscopic particles to chemical traces, protecting our health, dignity, and safety. By following nature's example and using advanced purification technology, we can now clean water so thoroughly that it can safely return to our taps, ready to drink once again. This process uses multiple proven stages of purification, such as microfiltration, which removes suspended solids and bacteria, reverse osmosis, which filters out dissolved salts and trace contaminants, and ultraviolet light and advanced oxidation, which destroy remaining contaminants. There are two main ways communities use these technologies. Direct potable reuse, or DPR systems, offer a fully contained, continuously monitored system that purifies and returns water directly to our drinking supply. Indirect potable reuse, or IPR, purifies the water before sending it to natural systems like groundwater basins or reservoirs, blending with other sources before being used and treated again. Either way, the result is water as pure as, or even purer than, what nature provides. It's a complete cycle. Water used, reclaimed, cleaned, purified, and renewed, ready to sustain life all over again. This is not the future of water. It's happening now. In many parts of the country and the world, we already drink purified, recycled water every day, safely, confidently, and sustainably. Every drop matters, because you and the environment matter. A future where everyone has access to pure, reliable water is a future where we can all thrive, and where every precious drop continues to give life again and again.
Hi, it is great to be here in person. For those of you who were at the March virtual meeting, we did, I think, what Dave referred to as Part 1, PFAS Part 1. This is PFAS Part 2, and it's not the end. We're right in the thick of things, right in the middle. So when we were here in March, we introduced the way that BWS is, or the approach that BWS is going to take to manage PFAS. So Sierra and I are back to talk more. Today we're actually going to take some time and revisit some of the questions that you folks asked in March. We thought there was a few that we'd like to answer more completely and dig into a little bit. So that's going to be the first part. And then we're going to further the PFAS discussion. And we're going to talk about how we're assessing risks to supply, PFAS risks to supply, and approaching long-term solutions. So these are the 4 questions that we're going to go into a little more depth of. We were kind of mindful when we took and chose the questions, because we had a really robust discussion that day, I think, and we really appreciated the questions, the comments, and the thoughtfulness of everything that this group was bringing forward. But we're sticking with the technical pieces more so than the health-related pieces, and there's a lot of resources around for information related to PFAS and health, and we've got some links in the end of the presentation here for that. So we'll talk about these first 3 briefly, and then that's going to lead to the rest of today's discussion around well site prioritization, the way we're prioritizing, and long-term solutions. And like I said, we're in the thick of it right now. We're not coming to you with a final anything at this point. We're starting. We're going to talk about what's happening with the initial evaluation of PFAS sources on Oahu, and talk about the technical assessment part of the island-wide PFAS management plan. So question 1, this was an Ernie question. Have PFAS concentrations in people been decreasing in the US? And, short answer, yes, the CDC has been tracking certain PFAS compounds in blood since the early 90s. In 2002, production of certain types of PFAS started decreasing, and aligned with that reduction in production is a reduction in PFAS levels in blood. And so, tough to read up here, but blood PFOS levels, one type of PFAS, have declined by more than 85% over a 20-year period, and PFOA levels declining by more than 70%. So I think this trend really, it really shows that regulating PFAS at the source and putting those in place can help to manage and limit human exposure. Another question that came up, what has Hawaii been doing to protect people from PFAS? And Hawaii's been really a leader in reducing PFAS in terms of product use and import to the state. And I think that's because, we're dots in the middle of the Pacific, and what happens here stays here, and we have to deal with it here. So looking ahead, we've banned Class B PFAS containing firefighting foam and PFAS in food packaging. So that happened in 2022. And currently, the ledge is looking at, through Senate Bill 683, which would expand PFAS bans to food serviceware, cosmetics, and personal care products. So the DOH also has established environmental action levels to look at guiding response to PFAS detections in drinking water. And we've conducted sampling in county, school, and private water systems. Also testing and sampling nearshore marine environments, local market fish, wastewater, Red Hill area, of course, and landfills. And that's going to give us an idea of PFAS here in Hawaii and where it may accumulate. Another question, how does PFAS level in the groundwater on Oahu compare to other areas across the world, around the country? So this map shows regulated PFAS around the world in drinking waters. And different countries regulate PFAS differently. Some look at the individual PFAS compounds. So if you look up here, China is in the green. So they measure or regulate PFOA and PFOS, just like the US does. Their regulation limits are 80 nanograms per liter and 40 for those two compounds. In the US, it's 4 and 4. Also regulated is, like in most countries, do a mix of these individual levels and then combined with cumulative levels. So of all kinds of PFAS or these kinds of PFAS, you can't be above, this certain level. And Canada and the European Union do this, and their limits are actually less conservative than the US limits. So US has some of the most stringent regulations for PFAS levels in drinking water around the world. How does PFAS level in the groundwater on Oahu compare to other areas in the country? There are somewhere around 150,000 public water systems in the US. Feels like we're still in early days yet because there's been about 10,000 of those tested for PFAS. But of those 10,000, about a quarter have detected regulated PFAS. So with those 2,400 or so that have been tested, more than half of those water systems are showing levels above the highest that BWS has ever seen. So we have a system that has had detected PFAS, but looking at the world and the rest of the country, it's comparable. So this last question is how do industrial processes and military operations, past and present, affect PFAS levels in groundwater? And that's just leading us into today's topic, where we're looking at introducing this group to the assessment of long-term risk. And I'm going to pass it over to Sierra, who's going to take a couple slides to dig into that one more. It's kind of the topic of the day.
So this is the question that we're trying to answer when we're looking at long-term planning for Board of Water Supply. So in March, we told you about the immediate priorities, which is this treatment at 3 sites where regulated PFAS was detected. there wasn't already treatment in place, and those wells were critical for the system demand. So that's immediate, that's happening now, but we wanted to dive into the long term, which is a little bit more trying to read that crystal ball, right, of where do we think it could show up in the future and how can we be prepared for that. The general process for that is these steps where we start by prioritizing the sites for where do we think PFAS is most likely to show up. Then we can look at, okay, what can we do about PFAS in those areas? So sometimes it's treatment. That's the common thing. That's what we're going to talk about today. But it's also, is there anything else we can do to prevent PFAS from showing up at that well? And then there is the process that BWS will do of actually implementing those things and monitoring and making sure they can be proactive instead of having to react every time this shows up. So the way we do that first step of prioritizing well sites, it's not an easy process, and that's what we wanted to talk about with this little equation here. So it consists of two main components. First, we have this potential sources. So we think of all of the different things that could release PFAS into the groundwater on Oahu. And then those get scored based on, how likely we think it is that it's actually releasing the PFAS. And then the second half is looking at the groundwater itself. So that's the geology, because it's not guaranteed that if there's a release, it will get into Board of Water Supply's wells. So that piece is looking at how likely is it if we have a little bit of PFAS here that it makes it into the actual well. Those scores go together, and that's how we assess the risk to that well. So we wanted to talk about especially this first part in detail today, because that's the work that's complete. This next piece, the groundwater modeling, is what's in progress. Don't try to read this map. I even got to zoom in on the map and it was hard to read. I think the main takeaway here, so this is just all the things that maybe could release PFAS. And so this is, DOD sites. This is also cesspools, anything where we know PFAS could be present and we say, maybe it could enter the environment. That's what this map is. And you notice it's a lot of points. That's the thing about PFAS. It's pretty widespread. Then the other thing to note here is the stars. Those are Board of Water Supply wells. So green ones, no PFAS has been found at those wells. Red ones, it's been detected. So good news, it's only at some wells. There's a ton of wells where we haven't found it, but we want to be aware of the potential sources near those wells. The other thing shown here in the green shading is these capture zones is what they're called. And the idea is water anywhere in that zone can get pulled into the well over, this is a 50-year time frame. And it's a model. We can't really know what's happening under the ground. But it helps us focus in where we don't have to look at PFAS everywhere. We have to look at sources in those same capture zones that could impact the wells. This is similar to what was done for the Source Water Protection Plan. I think you folks probably remember that. But this is a more kind of granular and detailed look, because instead of having to look at every possible contaminant, we're really dialed in on PFAS and focused on those sources. So this next map looks the same. It's not quite the same. Now the points are maybe more readable. It's color-coded. So not all of those sources are going to be equal chance of releasing PFAS into the environment, right? We know that like the firefighting foams, when they are released on the land, it's right there. It can go right into the groundwater. That's really different than maybe an industrial user who uses PFAS in their process, but isn't putting it directly onto the ground. So that's where this risk scoring comes into play, where the small points and the yellow points are kind of the lower risk, and then the red triangles are the highest risk sources. And so they're the ones that, we're pretty sure PFAS was released into the environment. You'll notice the red triangles don't necessarily line up with where it's been found in the wells. And that's because we don't have that geology component, or because this is really complex. We'll find out how much the geology helps us explain. But this gives us a sense. You'll see like a lot of the yellow points on here are cesspools. And so cesspools, we know there's some PFAS in them, but it's not going to be released to the same degree as we see with something like the firefighting foams at the much higher concentrations. So this risk scoring, it's not intended to kind of dial in on, oh, this one user is contaminating this one well, because you can see it's so many points. That'd be really hard to do anyway. The goal is to look for solutions and to plan ahead. And so we're summing up, okay, there are 5 sources in this area that could impact this well. We have different risk scores for all of them. We can add that up and say this is the total risk of PFAS contamination in this well. Yeah.
I think you've addressed what the Board of Water Supply is looking at really thoroughly. My question is, what can be done to help the Food and Drug, the EPA, to get in the game and do federal legislation to help control some of these issues?
Some of that is in progress. We are seeing regulations at sort of the manufacturer point. But yeah, if I knew how to make EPA do things, I would be doing things differently. Yeah.
I wanted to know if, with the geology issue, have you talked to the UH Water Resource Center? They might be able to help with some of your geology needs.
The models that we're using are developed by, I think some are out of UH, some out of USGS. And so it uses that same underlying information, and then it's just rerun and recalculated for this application. Wanted to mention the data sources that go into this because it is a lot of different databases that we're pulling all of this information from. The primary one is this Environmental Risk Information Services, which is actually its own compilation of spills, hazardous materials, things like that. But then also delve even more into the data, really looking specifically at different land uses, potential sources to really capture any imaginable source of PFAS. Summarizing that, what we just looked at was that potential source score. The next step will be kind of into the groundwater modeling. And then we're also looking at, it's primarily treatment projects, especially in the near term, because we know we might not be able to do anything to prevent PFAS from showing up in a well, so then we have to address it in that well. But the overall project will also look at other ways to mitigate PFAS. So wanted to spend just a little bit of time talking about what PFAS treatment looks like. For Board of Water Supply, we're basically considering 2 main technologies, so granular activated carbon or ion exchange. Both of these work the same way, where you have this media inside a vessel that removes the PFAS, and then eventually the media gets used up and has to be replaced. That's important because you can't just put something there and it mostly runs itself. Like, the operation and maintenance costs are pretty significant. The difference between the 2 medias, GAC is a little bit more general, so like it's already in place for some removing legacy pesticides. Ion exchange can be more selective for PFAS, which can often help it remove it a little bit better and last a little bit longer, but it means it can't help with other types of contaminants. So right now, we're putting in GAC systems, but the systems are designed to have either type of media in them so that Board of Water Supply has that flexibility in the future.
The slide, the spent media for the granular activated carbon landfill, or what does reactivated mean?
Oh, yep, thanks. So basically they put it in a big kiln and it burns off the PFAS and destroys it, and then that media can go back in the vessels. So that's the other advantage of the GAC, is that it's not necessarily landfilled. We wanted to briefly touch on costs just to give you a sense. So the 3 systems that are currently being designed, capital costs range from $6 to $20 million per system. That's because they're different sizes. And just to give you a sense of the O&M cost, so Cotamilo wells will be a 2 MGD facility. If it ran continuously, we're looking at just the cost of changing out the media, disposing of it, labor, everything, about $300,000 a year, which just in today dollars, no fancy math, is about $9 million over the 30-year period. So it is really substantial compared to the capital cost. I'm going to pass it back to Michelle to talk about kind of next steps.
Sierra has talked about the PFAS problem being complex and expensive, and the solutions also are complex and expensive. So we do need to go back to that prioritization to decide when and where to invest. And once our groundwater modeling and our hydrogeology analysis are complete, we can prioritize those well sites by the likelihood of impact, and that's going back to the maps that Sierra was showing. And then we can develop and program capital projects to reduce the risk and look at cost and the feasibility for an implementation and implementability of those solutions, which is going to bring us back to you at the next SAG meeting in July, hopefully with these guys looking at the master plan and talking about the PFAS projects in the context of the whole master plan as well. So wrapping it up, this is a schedule that those of you who were at the March meeting have seen before. It really it highlights the next steps that BWS is going to take to meet the MCL by the maximum contaminant limit for PFAS by 2029. There is talk of that deadline being extended, but as of now it is not, and so we're working towards 2029. For the 3 priority sites that are being designed, and that design will be complete by summer 27, which with treatment in place and water being treated by 2029, that to meet the deadline. We're advancing, creating an overall island-wide list of capital projects related to PFAS to align with the master plan schedules. And you can see that's sort of outlined in that orange. So you've got this initial PFAS project list for the master plan in the diamond, the far right diamond. You can see how early on that actually is in the detailed PFAS assessment and mitigation plan that we're working on. So that initial list is going to be based on the best information we have now, and as we continue to learn more, we're refine that over time. While we're working on the PFAS management long term, we're also working through addressing another emerging contaminant for this island, TCP, and one has come on the heels of the other. So that really highlights the uncertain or unpredictable nature of the contaminants and what we're going to find over time. So the management plans that we create to deal with PFAS and TCP is going to be the basis of the bottom line, which is a long-term framework to address future contaminants not currently on the radar. So when this happens again, or when we see things coming from the EPA, how can we do this more efficiently? So more than one positive thing is going to come out of this work. There's a few links here. You click there, Jicky. Yeah. Take a look. We'd love to have some feedback on this. Talking about risk is hard, and looking at that without creating undue alarm or fear, but still respecting the fact that people want to know. We'd love to have some feedback on that. And then, we've come in the middle, and so obviously there's gaps in the information we're presenting. But what gaps are there that could affect the way that the community sees, the BWS looking at PFAS and emerging contaminants? So some thoughtful things maybe we'll be able to ask you next time, but thank you so much.
Just a reminder about our next meeting. It's going to be back here in person on July 16th. I know we gave you a ton of information tonight. Hopefully you found it interesting and helpful and impactful. There's a lot going on as we go through this Water Master Plan process. So thank you for being here. Thank you for your participation, your interest, your input, and I'll see you all in July.